Okay, hi everyone. Welcome to today's webinar. Speaking to you live from Lagos, Nigeria. I literally have butterflies in my belly. Seems like it's been years since we had the last webinar. And funny enough, it's just been last week. So yeah, welcome. And due to the widespread of people from different time zones joining this webinar, sometimes I'll be lost for which greeting to offer, but then I would say good day, everyone. I'm connected to you live from Lagos, Nigeria, where it just rains, so it's pretty chilly and cold. So it's a cold weather, but then nonetheless a warm welcome. So welcome everyone. Uh, so as is our custom, we always love to hear from you and get feedback from you, as it is to help ourselves and help you to have a better experience. And over the course of the week, we started the open source projects, and we know that a lot of you have been engaging in it, and your groups have started working on different phases of the project. And I would like to hear your feedback on that front. So let me know how it has been, especially working with people virtually that you can see, and how you've been able to measure all of that and keep the project running. So basically if you want to share, if you want to share your comment, just raise your hand and I will unmute you. So basically tell us about your experience with the open source project. Have your teammates been cooperative? Have you been able to clean terabytes of data? Have you gone beyond terabytes? Have you cleaned a lot of data? Have you done so? What exactly have you done so far? It would be nice to hear. So, anyone willing to share? Hmm. Anyone? I can see a ton of people. I have Mabel, I have Asan, I have Happiness, and I know you guys have been really active, making pull requests on GitHub and everything. So I'm sure there are a lot of stories to tell, and I would love to hear them. Anyone? Are you guys shy? That is not a usual custom. Seems like the cold is affecting a lot of people. So you have a lot of shy people. You guys are just a bit cold. Okay. On that note, if we have no comments as regards the open source project, at this point, I'd like to turn the microphone over to Tobiloba Adejumo, my esteemed colleague. Thank you.
Yes, thank you, Femi. Hi, everyone. I am really excited to welcome you all to today's webinar. I see we have people already online on YouTube and Zoom. I am very delighted to onboard you today. You can use the live chat to let me know how you're feeling this afternoon. Currently in Lagos, Nigeria, it is raining with a temperature of 27 degrees Celsius. Now we have special appreciation to some special people. Shout out again to Oyedikachi Adigwe. She's the first to join the webinar on Zoom, and Oluwasome is the first to join on YouTube. You are our webinar rock stars for the week. Now, moving on very quickly to our housekeeping rules. If you have any questions, any posers, any linguistic propositions, during the presentation today, please wait till the end of the session to avoid lag or intermittent disruption during the presentation. You can leave your questions on Slido using the event code 73347. I repeat, you can leave your questions on Slido using the event code 73347. Now let's turn the table over to our speaker who is going to be talking about COVID contact tracing as graph problem. This is a subject in which we should all be acutely interested in because, as you know, contact tracing is one of the interventions that have been used effectively to control Ebola virus diseases outbreaks in Africa. Our speaker is the lead data scientist at the foremost airline company in the UK. What is special about him is that he has nearly 2 decades of experience in a variety of analytical and data science roles, both in academic and in the industry, working with highbrow organizations across the continent. As you listen to his presentation today, you will notice his subject matter expertise in NLP, that's natural language processing, big data and semantic web, and also graph data structures. With many accreditations, years of experience in data science, and a degree in cloud computing and computer science, today's session promises to be uber informative. Let's welcome Emmanuel Asimadi. Emmanuel, it's so good to have you here. Thank you so much for joining us today.
Thank you for having me. That was a lot of accolades. But yeah, I appreciate it. It's such a pleasure to be here. I will just mount my screen quickly. So you let me know if you can see my screen. And then we start the conversation.
Yes, we can.
That's good. Okay, so you are once again welcome to this webinar. It's always a pleasure to share knowledge, and today is just one of those opportunities where we get to share knowledge. My name is Emmanuel Asimadi, like Toby said. If you look me up on LinkedIn, EMML Asimadi, you'll find my profile there, and we can always connect and share knowledge. I'm open to new ideas and interactions. It is always in those interactions that we almost always find new knowledge and new ways of solving problems. So let's always keep interacting. Today's topic is an interesting one. We are looking at COVID contact tracing as a graph problem. Okay, so in this session, what I'm looking to do is to almost make you excited about this fascinating data structure called graphs. We will look at what graphs are, and then we'll then look at some of the concepts and terminologies around graphs, and then we frame a problem, a very basic problem of contact tracing as a graph problem, and try to answer the questions around contact tracing using the graph. Okay, so the idea is to almost show to you an alternative way of solving problems in data. Okay, there are many ways. People use SQL, others use machine learning, and graph is just another interesting way to organize data and solve problems. Okay, so once we get started, you should feel free to ask questions intermittently to make it quite interactive. I'll be, if you see the slide and you think you have a question, just feel free to message and ask those questions. But the first slide is asking the question, what are graphs? So if you are not familiar with this data structure, when they talk about graphs, you might be thinking about charts or visualizations or stuff like that. But graphs are essentially a data structure that organizes data into nodes and edges. Okay, so you have a node, which is like some structures call it vertices, and then the edge. Okay, so the edge is the relationship between the nodes. So it's a very basic data structure that is quite flexible and very powerful. Okay, so in a typical world, the organization of nodes, you have the node that probably will have a name and then can have any number of properties underneath it. So if you can just start guessing, the world is full of a lot of graphs. A typical example of a graph is your social media graph that Facebook will be talking about. So you look at, if we decide to organize the social media as a graph, then this node could be a person, and then the name of the person and other key value pairs will be properties underneath the person. And we can do a lot of queries, sophisticated queries, and also can do very sophisticated algorithms against the graph, which we'll see in a couple of slides. So you have the nodes that have their properties. The edges, nicely enough, can also have their properties. Okay. And that's essentially what a graph is. The graph in its most basic form is the organization of data as nodes and edges. But this is a typical graph that we call the property graph. There are other types of graphs, like the semantic web. that's also an organization of data in the form of a graph. We call that the knowledge graph. Okay, with the semantic web, it is the notion that we can organize data in a way that machines can reason about that data. Okay, so we put the data and line it up in a way that, typically in triples, they call it subject, predicate, object. We line it up in a way that when a machine encounters it, it is able to reason about it and infer new knowledge. This is a less popular approach compared to the property graph, because I think it's easier to organize data into property graphs and do stuff with it compared to doing what we call the semantic web. Just to highlight a bit more around, for those who might be interested in researching the area, the semantic web, a typical example would be like organizing locations. So you could organize locations in a way that you say you have Lagos is in Nigeria, and then you also have another triple that says Nigeria is in Africa. In your data set, you will not specify explicitly that Lagos is in Africa, but because we can specify that the relationship is it's a transitive relationship, the machine can infer that because Lagos is in Africa, the machine can infer that because Lagos is in Nigeria and Nigeria is in Africa, it means that Lagos, which is the leaf, is also in Africa without you explicitly specifying it. So those are the interesting attributes of the semantic web. It has logic together with the data. So when you organize the data in very nice ways, you can find interesting patterns. The emphasis of today's talk will be property graphs, like you have already heard. It's just nodes and edges, and then we do stuff with that. Okay, so why graphs? Graphs are interesting because they are a flexible data structure and they are easy to reason about. Our world is more organized around graphs than tabular data, which is what we usually use. So if you think of it, there's a lot of graph around us. The first one I mentioned is the social network. You could also think of other types of graphs, like transportation can be organized into a graph. Your data network is also a graph. You can think of your switches and other nodes that route traffic as nodes, and then the link between them as edges. Okay, so when you model your network as a graph, you can sort of ask questions. What is the shortest path from point A to B? You can also ask yourself, what happens if a node fails? What is the next shortest path? You can also ask interesting questions around the resilience of the network. So you can investigate the single points of failure and how failure propagates through the network. So those are just examples of what you can do, or how our environment is organized into graphs, okay? And then once you organize data into graphs, you have very powerful pre-existing algorithms to benefit from. And those algorithms, some you may already be experiencing in your search. That's what Google used in its heydays, called the PageRank algorithm, where we sort of look at different nodes and the connections they have and use that to rank them. So not necessarily the node that has the most connection becomes the most important node, but it's almost like a weighted way of ranking the nodes. It's one of the popular algorithms that are available in almost all graph structures. You have connectedness. That is a way of almost determining communities within your graph. So you want to see whether there are smaller subgraphs to work with. What makes it interesting to detect communities in your graph is there are a number of use cases, like recommendation is one of them. So if I can detect smaller communities within a larger one, I can predict how people belonging to the community will behave. So if there's a new association into that community, I can almost predict how that person will behave. I can also use that data because a community is formed. I can use that data to almost recommend items to people in the community. So communities are a way of what we might call customer segmentation, for example. So if I detect communities in a social graph, I can look at it and say, okay, because person A belonging to this community liked a certain movie, and person B belongs to the same community, I want to recommend that movie to that person B because they haven't seen the movie yet. And recommenders are very powerful ways of upselling when you are in an online marketplace. Okay, then graphs also lend themselves to very sophisticated queries, and you will see that those queries are quite intuitive. They are as close to natural language as possible. So sometimes when we are querying stuff, we want to express things in very sophisticated ways, but SQL falls short of that expressivity. Okay, so graphs allow us to query stuff very close to natural language. There's still, between graphs and natural language, there's still some gap, but the closest representation of queries that is almost like natural language is graph queries. And then it's very intuitive to model real world scenarios with a graph. So example, transport networks can easily be modeled that way. There's also they are strong at analyzing connected data. So if you have data that is about connections and how connections are and pathways, so to say, you can use graph data structures to analyze that. And that is why we are using this approach to almost think about how we will work with contact tracing as a graph problem. Okay, so the use cases are numerous. Like you said, there's fraud detection, there's best path through a network. So that's network analysis and stuff like that. Disease pathways is one of those that we'll talk about. Recommendation, that we can have movie recommendation or item recommendation as one of them. There's also social network recommendation. So if I see a pattern that I follow Femi on social media, and Femi also follows maybe Toby, the graph, we can draw up a query that allows me, because of that chain, to recommend me to follow Toby or Toby to follow me. Okay, so we can use the graph to detect missing links and propose those links or recommend people to follow on social media. Then there is also the interesting use case, which is relatively new. That's that using graphs as context data for machine learning problems. I have links to the blog post here. I have link to a book here that uses that. Graph is very rich in presenting complex data. You can actually derive very complex patterns from graph. And the theory or the philosophy that Neo4j is following now is that they are able to leverage these complex queries and use that to drive the machine learning algorithms that we are already familiar with. So regression models, your XGBoost and all that. Instead of picking data directly from a flat file or a table, they allow you to almost draw up your own query, very powerful query from a graph, and then use that to drive your machine learning model. So that is almost I think might give you a slight edge over what you can do with your machine learning model. This is because graphs in themselves are so sophisticated that you could solve your typical machine learning problems with graphs and be equally successful. So the combination of graphs and machine learning models would be interesting. Of course, networks are everywhere. So the kind of problems you can solve are not limited to only this. You can solve any other problem that you can frame as a graph problem. You can solve it with these approaches. The interesting part is that graphs are just abstractions of nature or of your observation. So the way you organize the graph is dependent on the problem you want to solve. So somebody given the same environment or the same scenario or problem, two different people might organize their graphs differently. But the goal is not about a perfect graph, but it is about a graph that is suited for the problem you want to solve. Okay, so there are a number of graph processing platforms. So they are typically grouped into two types, depending on where the emphasis is. So if the emphasis is on graph computation, okay, that's like how you collect all the data in the graph and do some computation like page rank algorithm or shortest path or a kind of a search from node A to B. If the engine is focused on computation, then we have that class called the graph compute engines. There are also other graphs that are focused or are more like databases, and Neo4j and these types of graphs fall in that category. So if your problem is computationally intensive, you are going for the likes of Apache Spark with its internal graph frame or GraphX data structure in there. Or if it is more of a online transaction querying and just attaching to a small part of the graph and doing something in memory, you are more tilted towards the database types, which is a Neo4j. There are a lot more examples of graph databases. These are just a few that are interesting. So Spark is particularly interesting in the sense that within the Spark framework, in addition to your graphs, you have your machine learning algorithms in there that when you query your graph in your complex way, you can now continue a pipeline that will allow you to do regression, that will allow you to do some decision tree or some kind of a random forest or any other machine learning algorithm on top of your data. So Spark being a unified platform is very interesting in this space. And Neo4j, which is the platform I'm using for a lot of the demonstrations today, also is interesting because of the way it visualizes it and its powerful query language called Cypher. Okay. So, like we looked at, I'm sure you are already familiar with it, but I just wanted to cement the understanding of what a graph is. So this is an example of a basic graph. So in Neo4j, and this is more tilted towards Neo4j, in Neo4j, a graph can have a label, can have 0 or more labels. So in this example graph, you can see that this is a node, and this is the edge. There is another node, an edge, and then a node. Okay, so just to recap, the node is almost what we call the vectors. It's in graph analysis, they typically call it the null, but it's the entity that you have in your domain. Okay, and depending on what you are modeling, something can be an entity or the relation itself. Here I'm modeling a person being in a medium. Okay, so the label and in nodes have labels. They can have 0 or more labels. Okay, and they have properties. So those properties can be any key value pair. Okay, so that gives you significant flexibility around what you can put underneath the node. And when I label this as a person, there is no, it's not mandatory that I have the same key value pairs underneath the person. Okay, so I can have name here, I can have age here, and then here I have profession, but you notice I don't have profession here. Okay, so that's an interesting thing. The nodes have labels, and underneath those labels, you have key value pairs, and you have the flexibility of putting any key value pair underneath it. Same as the relationships. The relationships are what we call the edges between the nodes. Okay, so I have a relationship here as was in. Okay, and that relationship can have any key value pair underneath it. And if you guess right, you probably will see that an interesting key value pair would be date, for example, here. So this person was in the bus in a certain date. And then there's another person called Kofi, who is 65, was in a bus, and we can put any key value pair on the edge. Now, the interesting part is that all these data you see in the graph are queryable. Okay, so we can now say, I want a person by name Obi. And I want to know who Obi sat in a bus with. Okay, so you don't even know whether Obi sat in a bus, but you know there is a relationship was in, and you can just find who Obi sat in a bus with. Okay, so some of the graph algorithms are like, there are 3 main ones. There are those that are interested in finding paths. So they find the shortest path in a network. Some also find you can have queries that find all paths between 2 nodes. Okay, and there are very interesting ways of modeling the network. So if you are modeling a transport network, your city could be one node, this could be another city, this could be another city, and the edge could be congestion or traffic between these 2 nodes. The weight on the edge could be that. And so if you were to find the shortest path with the weighted edges, you can now say that, okay, actually going from city A here to city B directly is more expensive than going through a second city, because the edges have weights. So there are very interesting things you can do with graphs. And then there is the concept of centrality. Okay, centrality is trying to find important nodes in the network. So things like using PageRank is a way of finding important nodes in the network. So PageRank in a social network will almost rank people who are more influential, and you can use that to do stuff. Okay, so what is an important node in a network? The notion of importance varies depending on what you want to solve. Okay, so for some problems, importance is just how many entities are connected to you. Okay, and that is a problem we call the degree. So you can look at how many entities are following you, or it may be how many you are following. Okay, so the importance could be just the number of edges you have. So we can say that this entity here has the most number of edges. That's why it is the most important. Your importance could be also that a certain entity in the network is the single point of failure. So it is in the middle of the network, and if it doesn't exist, there will be two separate subgraphs. So that's another way of defining importance. So there are different algorithms for finding such nodes in the network. And when you find them, you can do stuff with it. There is also community detection. So you have a graph that has smaller communities in it. You want to find how many communities are there and also do some stuff with it, because communities are people or entities in the graph that have things in common. Okay, so you can use algorithms around connectedness to detect communities. Okay, so in Spark, for example, when you find the communities in it, it labels each of them with an integer 1, 2, 3, 4, and you can work with it. Okay, should I pause for some questions on the half-hour mark? I should keep going. So we are looking at contact tracing itself as a graph problem. So this is the last lab, hopefully. So what is contact tracing? Okay, the problem of contact tracing, and this is not for COVID alone, any infectious disease is, and like Toby said, like Ebola, given that person A is diagnosed of an infectious disease, we want to find all people or media they have been in contact with and potentially infected. Okay, so given that person A joined the bus today and a day after we diagnose him of COVID, we want to find everybody who was in the bus, including knowing which bus he took, so that we can take mitigating measures and ask people to self-isolate to break the chains. Okay, so how do we organize this as a graph problem? So Subtac on LinkedIn just shared this interesting image of how contact tracing should work. Okay, so you have person A and B living in a house. So we can say somebody and the family member, and then person A joins a train to work. Okay, so person A joins a train and all, like is the same train with C and D. He goes to work with E, F, G, who are close to him, and then there are people H, I, who are further away from him. And then from there, he comes back home. From work, he comes back home. Okay. The problem of contact tracing says that if person A wakes up in the morning and gets symptoms and is confirmed to be COVID, what we want to do is to signal persons B, the person he was at home with, C, D, E, F, G, H, all these people he has been in contact with. We want to signal them for them to self-isolate. The other thing we want to do is to find all the media he has been in contact with so that we can decontaminate it. We can, especially the common areas. So if it is a bus or a train and work, we want to decontaminate that media. For those who are not too close to him, we might tell them to do social distancing or lower their contacts so that the risks of infection, or we can cut the chain of transmission. Okay, so this is a fairly well-defined problem, but it's not usually easy to solve. Now, we can organize it as a graph problem. Okay, so if we decide to represent what you saw here as a graph, this is how that graph will look. Person A is at home with person B. Person A takes a train with CD. Person A was at work with EFGH, and then he came back home to meet person B. But just for interesting illustration, I've added that they got a visitor called person J. And then there are, of course, people who do nothing in the network. They just don't go anywhere, like person K and person L. So that's a simple representation of the graph. And when you are building a graph, you typically you define your vertices, which are the nodes, and then you define the relationships. And this is common across any graph data structure you ever build. You define the vertices or the nodes. So in this case, we are defining a person called person A. We are defining the key value pairs underneath them, including their contact, including whether they have pre-existing conditions. And we are flexible on what we can put underneath it. It just has to be a key value pair. Okay. And then we have all other people in the network and their contact. And then we have the relationships in the network. So it's fairly straightforward to build a graph, to define a graph. Of course, in the real world, we will probably be importing this data from a SQL database or a CSV file. In actual contact tracing, building this graph is not trivial. And I think it is the most difficult part of contact tracing. And there are apps that are coming up that might enable us to do such things. So the Google and Apple have come together to enable a way of building this type of connections. So when you come into contact with somebody, they enable the apps enable communicate via Bluetooth to almost store the details of the person you have come into contact with, so that in case you are person A and you become positive, the app can notify all other people you have come into contact with. Even with that, it's still not trivial to build this graph. The biggest part of solving the contact tracing problem is building this type of graph. If you take the Bluetooth example if you take the Bluetooth one, for example, the range of the Bluetooth could be more than the distance that it would take for you to be contaminated if you come into contact with somebody who has COVID. There's also an interesting case of if I'm working in the same office and I am separated by a wall. That with Bluetooth, if I'm next to somebody but we are separated by a wall, our phones might communicate, and that will give us a false positive. So we could have a physical barrier between us, but the phones will communicate and make it look like we came into contact. Okay, but for the lack of a perfect approach, the Bluetooth seems to be the best way to generate this type of graph. Okay, there is also you can have people talk to, like, technical contact tracers talk to people and then feed data that will generate this graph, but that will be a lot manual. Okay, now the interesting bit is running the queries. So the simple query of we have diagnosed person A of having COVID. Who has he been in contact with? Is that straightforward? So person A, we are interested in match person A who was in a certain medium. We don't know the medium, but we know he was in that medium. When you match this, find all persons which we are labeling P1 inside that medium M. And then you return all of them. So we return both person A and every person that has been in the same medium. And this is the subgraph that you return. It's fairly straightforward. And you notice clearly that these two people who were not in any of those medium do not appear in this subgraph. Okay, so it's straightforward to almost extract the contacts of person A in a graph model. Okay, then you probably will be asking me, Emmanuel, we are not talking about nodes. We want the contacts. That's why we talk about it as contact tracing. So it's almost trivial once you can attach to the node. So once we know we are looking for persons, which are P1, you have P1, their name, you can get their contact, you can even get the medium in which they were contaminated from. Okay. And these are people you can just contact and say, hey, hello, just self-isolate, or you can send them an SMS. Okay. There is also additional things you can do because you have organized the data into graphs, like which media is most contaminated. And that is also a fairly simple query. The same query, we are matching that, but in terms of contamination, we are just saying we are counting the number of people in the medium. So given that the medium is contaminated with person A, tell us how many people are in that medium. And then my time is up. Unfortunately, I'm done with that as well. So we have, I have listed some references. These are graph algorithms, a book about just interesting graph algorithms that you might find interesting. There is also a book around graph-powered machine learning. You will find that interesting as well. This is almost like forward-looking, how you can use graphs together with machine learning models to do stuff. And then this is a blog about Neo4j using graph data structures for machine learning. So in Neo4j, you have the ability to use Cypher. So the language you saw here, this language is Cypher. In Neo4j, you have the ability to use this Cypher language together with inbuilt data science library in Neo4j to do machine learning on top of graphs, which I find also interesting. There are more sophisticated things you can do with graphs. I'll leave you to find those out. And I hope I have been able to almost pique your interest in investigating graphs as an alternative solution to data science problems you face. Thank you very much. I'll pause for questions.
Wow, this was really educative. Thank you so much, Emmanuel. I loved your style of teaching and how you were able to, break down COVID problem as a graph problem.
Thank you.
And I also loved how you pointed out two areas of research, the property and the semantic web, and looks like something that I might, study after this session. Looks like we have some questions here already. So this is a particular question from an intern. Graphs give magnitude of a quantity, although it expresses things in sophisticated ways, but it doesn't give the precise qualitative analysis. Does this pose a serious disadvantage in contact tracing?
Yeah, so you're saying graphs are not quantitative enough or qualitative?
Qualitative.
Qualitative.
Yes.
Yeah. So that, quantitative graphs would be precise if, when we model problems, we try to model them as best as we can to represent the ground truth. Graphs, being mathematical models, would try to be very precise. The difficulty you have with graphs is almost standardization, I think, that somebody modeling the same problem will model it differently from another person. In terms of doing stuff qualitatively, when you talk qualitative stuff, it means you have a human element in it and you have subjectivity in it. And subjectivity and mathematical modeling, you can use both together to help your thinking, but they are different concepts. I think graph is typically mathematical. They are models that you build to solve your problems. I don't know if I've really addressed that question, but I wish we could hear from the person to understand what they are actually driving at. But that problem you mentioned, if graphs are suffering from it, tabular data structures or other data structures will suffer from it more because graphs are more flexible than other data structures. So if you are looking at data structures, you come from a spectrum of the basic SQL tabular data. Then you have graphs. In terms of flexibility, you have tabular data, you have graphs, and you probably have JSON or documents. And then at the end of the spectrum, the most expressive and natural one is natural language. Okay, so natural language can be qualitative, but when you go this way, you become more precise.
Okay, thank you so much, Emmanuel. Here is another from Abdul Quadri on Zoom. So he's asking, the concept of these graphs remind me of Cisco in The Flash. Okay, that's a movie. Which brings me to the question.
Yeah.
How scalable is the concept of graphs applicable to center of crime detection?
Yeah, good. So that's a nice question as well. So in terms of graphs, now and graphs are also following what tabular data has the limitations tabular data had. In the past, tabular data could only be kept in a big one single server. Okay, and the concept of big data allowed us to now have distributed servers to store tabular data, and then we now have the concept of big data. Graphs are now allowing themselves to be parallelized. Okay, so you can have the data stored on multiple nodes. That means you can really scale, especially if you have the platforms like Spark. They allow you to store the data in a lot of nodes, and you can scale because you are able to process in parallel. There is also the one that Cassandra is also a data platform. It allows us to also, I think they are using TickUp. They also have distributed graphs. So the graph is not stored on a single node, it's distributed. Those type of graphs scale properly. There is the limitation of Neo4j is the fact that it's a single node type of graph. So all the graph sort of resides on one machine. But their advantage, they also talk of different advantages that they can read and write faster in that approach. So depending on what you are doing, you might go for one that is a machine gun or one that is a pistol.
Okay, thank you so much, Emmanuel. Here's another from Jolomi on Zoom. How are differences in time zones captured in graphs when doing contact tracing?
Okay, so in terms of modeling, it depends on the user's preference. Okay, if I am modeling for graphs, it can quickly get complex. It can quickly get complex, and so you will put only things in the graph that you think you will need. Okay. Having said that, if you want to model time zone, we can always use the universal time. That is a UTC. And so you transpose everybody's time to be the same UTC. So if you decide to use GMT, you use GMT for everybody, and we probably can work that way. But in graphs, you put only things that are relevant to your problem. So it's whether date and time, of course, date and time will be relevant to your problem, but yeah. So if you put it, date and time will be relevant. So just keep it to UTC, make it common.
Okay, so Jolomi, keep it to UTC. And another question here. I am currently working on time series project as my open source project. Is it possible to make use of graph to build my model?
Okay. So time series analysis. Yeah, time series analysis has quite some advanced concepts in there. I haven't tried using graphs to solve it, but the question could be deeper than, the question needs something more for me to be able to say whether you can use a graph to solve it or not. But yeah, time series, they probably have very mature concepts in there already that you can use in terms of time series analysis and anomaly detection.
Okay. And the next one sort of borders on the previous one. So it says, please, can you give me examples of deep learning problems that can be solved using graphs?
Yeah. So the problem of recommendation is one that graph solves very nicely. So recommendation is one of them. That's one. Fraud detection is one of them. But deep learning is mature in the space of, it's mature in the space of image analysis and natural language processing. And those are not things you represent as graph problems. So yeah, it's yeah. I think that should answer it.
Yes, thank you. Even this part, the next question actually also borders on the previous one. So the intent is asking, what is the future of graphs in deep learning as of today, as deep learning's model can only satisfy traditional flat or sequential data delivery.
Yeah. So in terms of so what graphs do, and for the things that Neo4j and the likes are doing in this space, is that graphs give you a higher layer of abstraction or additional power to extract data into your machine learning model. So features that you struggle to build from tabular data, you probably can find it easy to extract them. They will eventually become a matrix or something that you pump into your machine learning model. But graphs give you more power to create features into your machine learning model. Graphs in themselves can solve complex problems. So I think if you make use of graphs in the right way, you might not even need the deep learning side of things. Having said that, we think that the solution space for general artificial intelligence is going to be a combination of that. It's going to be a combination of something like semantic web and then something as powerful as deep learning. Okay, if you think of it, semantic web is almost like knowledge representation. The way our brain works, it processes knowledge and stores it in a certain representation. Our eye is almost like a deep learning network. Okay, so it sees something and it recognizes it and represents it in the brain. So a combination of the graph network that has the logic and knowledge representation, and then the complication of deep learning, which is a narrow, is what is going to get us into general artificial intelligence. It is not a solved problem.
Okay, and this also brings me to this question, and it seems like you've already answered it anyways. I see applications of graph data structure in machine learning as very challenging because it is difficult to store huge graphs in a tensor to feed an algorithm. Please, how can this be solved?
Huge graphs in a tensor to
feed an algorithm.
Yeah, so you don't need to store the graph in the tensor. Okay, so what I think is you have the graph existing, like there are even a lot of graphs like the Yelp review data set. It's a large graph that is public and stored. It already exists. The graphs exist, but to go into deep learning, you use the graph to select the features you are interested in and take it into your tensor or your deep learning algorithm. So you don't keep the graph inside the tensor. The graph is like a table or it's like a flat file. But the graph has more power in terms of the features you can generate from it or the relations you can extract from it to power your ML.
All right, thank you, Emmanuel. And there is another one from Oluwaseyi Akinkumi on Zoom.
Yeah.
So given the definition of a graph, having nodes and edges, can one categorize neural networks as graphs?
Yep. It's a graph. It's a graph. It's a powerful graph in itself. So a neural network is also a graph. The node is what does the computation, and then the edge is almost like a link to another node. So it's a graph. The brain is a graph. Like I said, there are graphs everywhere. You just have to, if you think of a problem and you can solve it with a graph, there's almost no limit on how you can model it. So there are a lot of graphs, and when you start thinking about it, you see graphs everywhere.
Yeah, thank you, Emmanuel. Now, here brings me to the last question. So, is there a maximum amount of nodes, labels that can be displayed on a graph?
Displayed, okay, yeah. Displayed, yeah. So it depends on the visualization tool, but you don't want to display everything you have. There's no value in displaying it because your perception can only pick a limited amount of information. But there are tools that display graphs very nicely. I think I saw some a couple of days ago, but you can really display a lot of it, a lot of data in some modern tools. What you want to do with graphs is to crunch the data with some computational algorithm to give you an answer. Okay. And if you want to display, you probably are going to be displaying the subgraphs, not the full graph. So I can show you, if we had time, I can show you the linked data set, which is a very massive, sometimes not particularly used data set that is linked and is just made of graphs. It's massive and we try to display it. If you don't abstract away from the details, nobody can make sense of what you have displayed.
Awesome. It looks like we've covered a lot of questions today, and we are almost past our time. Is there anything that you'd like to say before a final wrap up?
Yeah, it's just a nice meeting you all. I hope I've started some interest in you that you might explore later and make use of.
Yeah, and before we go, there is a comment from Ekemini on YouTube, and he's saying this looks interesting. So I think we can call it a day. Thank you, Emmanuel. Thank you, everyone. We appreciate you for being here today. Thanks for joining us, and we'll see you another time.
Yeah, have a beautiful weekend.